The word probability refers to the likelihood that the result of some event will be a given outcome. If the outcome is sure to happen, then the probability is 100%. We often use decimals instead of percentages to describe probabilities, so this is equivalent to saying the probability of a for sure certain event is 1. For example, it's pretty safe to say that it is 100% certain that you will not learn an entire new language fluently during the next 2 seconds. What about a so-called fair coin, which is a coin that is equally likely to land heads as it is to land tails? It will certainly land, so if it must land in one of those two conditions, each probability must be 0.5 or 50% or 1/2. But suppose that the probability that it lands standing up on its edge is 2%. What is the probability that it will not land on its edge? The probability is whatever is left over, 100% minus 2%, or 98%. The probability that the coin will land either heads or tails is 98%. If this is a fair coin, then of this 98%, half, or 49%, is the probability that it will land heads. 49% is also the probability it will land tails. Notice that the sum of the probabilities of all possible outcomes must always be exactly 1, or 100%, since this covers everything that could possibly happen. One way we can graphically represent probability is with a Venn diagram. You've used these a lot in the past, so this is just a quick review. We use shapes, usually circles, but could be any shape, to represent a set of data. In orange, we have the set of all mammals. We add more shapes to represent additional data. This time we'll add a blue circle representing animals that fly. Notice that there is an overlap between these two circles. This region represents the members of one set that are also members of the other set. In this case, we have mammals and animals that fly, so the only thing that would be both would be bats. We can use a Venn diagram to illustrate some basic concepts of calculating probabilities. Here we have a classroom with 20 students. The red box contains the 9 students who are in band. In the green box, we have the 4 yearbook club students, and in blue we have 3 football players. This leaves 6 students not involved in any activities. If we were to ask a randomly selected student to stand up, what is the probability that the student is in band? Since there are 9 students in band, the probability is 9 out of 20, or 9 divided by 20, or 0.45, or 45%. We use the notation P of B to mean the probability of B. We have 4 students in yearbook, so this is 4 out of 20, 1/5, 20%. There are 3 football players, and 3 out of 20 gives us 15%. Then we have the 6 that are not in any activities. 6 out of 20 is 30%. But wait, this adds up to 110%. The reason for this has to do with the overlap between the yearbook and the band students. To explore this mathematically, I'm going to introduce the logic terms and or. We'll start by looking at the probability that the random student is in both football and yearbook club. When we say and in probability, here we mean that the probability that both F and Y occur. P of F and Y means that the probability that a random student is in both football and yearbook. And is really the intersection, which in this case happens to be 0% since football and yearbook don't overlap at all. This means that there is no chance that a randomly selected student will be in both football and yearbook. Looking at our diagram, this should be pretty clear. When we say P of F or Y, we mean the probability that our random student is either in football or in yearbook. This appears to be just the sum of the 2 individual probabilities, the 15% in football and the 20% in yearbook, making 35% in football or yearbook. Now we'll see what the probability of band and yearbook is. Since and represents the intersection, we see that we have 2 students in both activities, so P of B and Y is 2 out of 20, or 10%. If we try finding P of B or Y by simply adding 9 out of 20, or 45%, plus 4 out of 20, or 20%, we get 65%. But due to the overlap, this double counts the 2 students that are in both activities. To make the correct calculation, we have to subtract the overlap from the total. The result is this formula, which says that the probability of A or B is equal to the sum of the individual probabilities A and B minus the overlap P of A and B. We can look at our 2 scenarios now with this formula and see how it works in both cases. Without overlap, as in P of F or Y, where we subtract 0, and with overlap in the case of P of B or Y, where we subtract the overlap. Another kind of diagram is the tree diagram. A tree diagram works best when there is no overlapping of outcomes, as with Venn diagrams. We start with an event and branch off to the possible outcomes. Here we have a fair coin toss. We expect that half of the time, 0.5, we get heads, leaving 0.5 for tails. We're not including the edge this time. Now, regardless of which way the coin ended up, we will flip it again. This time, too, we have equal chances, 50-50, of getting heads or getting tails. Notice that each time the tree branches, the probability of the branches have to add up to 1. We can find the probability of any one outcome by multiplying the probabilities along all the branches leading from the start to the event we're interested in. In this diagram, no matter which outcome in blue we choose, the probability is 0.5 times 0.5, or 25%. Let's look at a similar tree diagram that's not quite so symmetrical, which should help illustrate how tree diagrams are used. You play goalie on the soccer team, but another player also plays goalie. You have 2 coaches, Sam and Alex, who decide who plays what position during any given game. Sam coaches 60% of the time, and Alex coaches the remaining 40% of the time. Sam thinks both of you play goalie well, so he just flips a coin before each game and decides who to play that way. So with Coach Sam, you have a 50-50 chance of playing goalie. Coach Alex, on the other hand, doesn't think you are all that good, and so you only have a 30% chance to play goalie when he coaches. The other 70% of the time, the other goalie plays. So Sam coaches 60% of the time, and of that time, 50% of the time you play goalie. That amounts to 0.6 times 0.5, which is 0.3, or 30%. But Alex coaches 40% of the time, and of that time, you play goalie only 30% of the time, for a total of 0.4 times 0.3, or 12%. So overall, you have a 30% plus 12%, or 42% chance to play goalie, 58% chance not to. Notice that all possible outcomes total 1, or 100%, as they should.